Welcome to this session on classification. In today's lecture, we are going to look at the classification problem as a supervised learning problem. So the idea of supervised learning, if you remember from the last session, if you were there, is that we are trying to teach the machine how to understand the underlying pattern. So there are a few features or predictors, and based on that, we have a response. Now, the idea is that for each value of the predictors, we tell the machine the right answer or the right response. And as we give more and more information to the machines, the machine uses only the predictors and the value of the responses to understand the underlying pattern. And that is called machine learning. In regression, the response variable used to be continuous. But for classification, the response variable is discrete. Rather, the response variable can be different classes or labels. So suppose you have some incoming emails and the predictors are different features of the email. For example, does the email ask you to pay some money? Does the email ask you about your last holidays? Does the email ask you to buy something? And so on. So based on these features, we might try to classify the emails into spam or normal, or not spam, that is. So if I say that 0 can be interpreted as not spam and 1 can be interpreted as spam, then the discrete response 0, 1 can be interpreted as the labels or classifications corresponding to the emails. With respect to this classification problem in today's lecture, we are going to talk about 3 main classifiers: naive-Bayes classifier, decision trees, and random forests. If time permits, we might talk about a 4th classifier, which is a nearest neighbor classifier. If we do not have enough time, we are going to consider this topic in a later session. So first of all, let us try to understand the first classifier, that is the naive-Bayes classifier. The reason this classifier is called a naive-Bayes classifier is, first of all, it is based on the Bayes theorem. As a quick recap for what is the Bayes theorem, imagine that there are 2 events, A and B. Let's take a very easy example. Suppose we are rolling a fair die. So there are 6 possibilities, 1, 2, 3, 4, 5, and 6, right? Suppose event A is the event that once we roll the fair die, 2 appears on top. And B is another event that is, say, an even number appears on top. Suppose we are trying to find the probability that event A occurred. That is, we rolled a 2. The answer is 1 by 6 because there are 6 possibilities that are equally likely. But suppose someone tells me that after rolling the die, we already know that it was an even number. Now, if I try to find the probability that the number is 2, then notice that the probability is no longer 1 by 6, but 1 by 3, because there are only 3 possibilities, 2, 4, or 6. Since I already know that the number is even. This is exactly the idea of conditional probability, or rather, the probability that event A happened given that a different event B has already occurred. And the formula for that is probability that the event A and B occurred together, and this symbol is the intersection, divided by probability of B. Now, notice that if I flip the positions of A and B, that is, suppose I'm interested in finding the probability that event B happens, given that event A, then the formula changes to probability of B given A is equal to probability of B intersection A divided by probability of A, because I simply interchange the roles of A and B. But Since probability of A intersection B is, well, same as probability of B intersection A, I can write probability of A intersection B as probability of B intersection A times probability of A. And the denominator remains the same. So if I am trying to find the probability of A intersection B, but I already know the probability of A, probability of B, and probability of B intersection A, then I am good to go. And this property of the Bayes theorem is what is used by this Bayes classifier. The reason it is called a knife-Bayes classifier will be clear very soon. So in this problem, the different classes play the role of the A here. And the different predictors or the features play the role of B. So if I use this formula here, probability of C, where C is a fixed class, for example, spam, given the different email features, can be written as probability of the features given the class times the probability of class divided by probability of the features. The knife portion comes from the fact that the assumption made by the knife-Bayes classifier is the independence among the features. What it means is that the presence of a particular feature, say x1, is completely unrelated to the presence of another feature in the same class. This is why probability of x1, x2, x3 up to xp given C, which is this expression B given A here, can be factorized and can be written in a product form as given here. It's equal to probability of x1 given C times probability of x2 given C times so on. Further, notice that I have not written the denominator here, and I have only written proportional. There's a reason for that. The thing is, the idea for knife-Bayes classifier is to calculate the probability of a class given the different predictors for each of the possible classes. So I'm going to calculate the probability of spam given all the features and probability of not spam given all the features. And I'm going to see which probability is higher. This probability is also called the posterior probability of the class given the features. And we choose the class with the highest posterior probability. That becomes our prediction. So notice that when we are comparing the posterior probabilities for the different classes, the denominator is always probability of the features. And that is the same denominator for all the probabilities. So we don't need to worry about the denominators and only compare the numerators. So what happens is, because we can ignore the denominator, we do not need to calculate this probability. And because of this independence assumption, we can factorize each of these terms and calculate the conditional probability of the feature given the classes separately for each of the features. Now, this assumption is a very strong assumption. So the results of knife-Bayes classifier are often a little inaccurate because of this strong assumption. Because in general, in real life, the features are often really interdependent among themselves. We cannot assume that they are completely independent among themselves. But the results are still quite robust, quite usable. Maybe not the best possible, but quite usable. But the positive here is that it's extremely fast. So when you need very quick computations, you can use the knife-Bayes classifier to perform your classification. Now, this overall theory of Bayes classifier that we just talked about using the Bayes theorem, let us try to understand that with an example. For this example, I just have one predictor or feature, and I'm just going to explain how we use the Bayes theorem to make a classification. So in this example, the feature are weather forecasts. So we have three kinds of weather forecast: overcast, rainy, and sunny. And based on that, we have data on 14 days where the players have made a decision based on the weather to either play or not. So if I can summarize this data into this frequency table, Notice that there are total 14 days, and the players decided to play, which corresponds to yes, on 9 out of these 14 days, and did not play on 5 out of the 14 days. Out of these 14 days, 5 of the days were sunny, 5 of the days were rainy, and 4 of the days were overcast. And we have also split these days according to the final outcome. That means 3 out of the 5 rainy days, the players decided not to play, and 2 out of the 5 rainy days, the players decided to play. So this is the frequency table, and this table is going to make it really easy for us to make the calculations on the probabilities. So the question here is, suppose tomorrow's weather forecast is sunny. We want to make a decision or a prediction on whether the players are going to play tomorrow or not. So what we are going to do is we are going to find the probability of playing given that the weather is sunny, and we are going to find the probability that they are not going to play given sunny. And we are going to find which probability is higher, and that is going to be our prediction. So using the Bayes theorem, so yes plays the role of the A and sunny plays the role of the B. So we are going to use the right-hand side of this equation, and we are going to calculate probability of sunny given yes times probability of yes divided by probability of sunny. Notice that, as I talked about before, the denominator in both these fractions that we are comparing is probability of sunny. So while comparing, we don't really need to calculate probability of sunny. But since this is just a toy example, I'm going to calculate the exact probabilities and see how we work through it. So the first one is probability of sunny given yes. So if we go to the frequency table, we know that the players played, that means the outcome was yes, on 9 days. 3 out of these 9 days were sunny. So the probability of sunny given yes is 3 out of 9, which is 1/3. Probability of sunny. Now, probability of sunny is 5 out of 14 because out of these 14 days, 5 of the days were sunny. And next, probability of yes. Well, 9 out of the 14 days were the days where the players decided to play. So the probability of yes is 9 out of 14, which is 0.64. So if I do the arithmetic now, we are going to see that probability of yes given sunny is 0.6 and probability of no given sunny would be 0.4. Well, in this case, there are only 2 options. And clearly, because probability of yes given sunny is higher, then we are going to predict that tomorrow the players are indeed going to play. Now let us try to take a different example using the iris dataset. I'm going to use the iris dataset multiple times in this session. So let us try to understand what this dataset is about. First of all, this is an inbuilt dataset in R, and it's a very commonly used dataset for classification. So in this dataset, there are 150 flowers, iris flowers, and there are 50 of 3 different species of the iris flowers. So there's setosa, virginica, and versicolor. However, when we work through this example, we are actually going to use R. Well, since there are 50 samples of each of them, we can see that we have 4 features: the sepal length, the sepal width, the petal length, and petal width. So these 4 features become the 4 predictors, and the corresponding species become the response. Now, before we go any further, we should remember that while evaluating a model, we should always make the evaluations on a data that's different from the data where we trained the model. And this is something that we talked about in the previous session as well. So we should split the data usually between training and testing. In this example, I have done that. If you are running through the codes, make sure that you click through each of the cells here And this particular cell, especially for installing the package current, it might take quite a long time. So if you have clicked on it, please be patient. It might take a few minutes. But for now, let me just work and keep working through the example. So there are many ways of splitting the data set into training and testing. In the last session, we had looked at the sample function. Just for a variety, I have used a different function, the sample.split function that is in the CA tools package to split the data. And then I've divided the data into training and testing based on that. The idea is I'm going to train this knife-based classifier only using the training data. And then I'm going to look at the performance of the model on the testing data. This is to prevent overfitting. Now, the knife-based model, when fit, is used using the function knife-base. This particular function is in the E1071 package that we are loading right now. And notice that the data that we use here is train_CL, which is the training data only. The idea of knife-base is, it's like the structure is very similar to when we were working on the linear models in the last session. We have the response, which is the species, given, or the tilde function, the predictors. Since in this data set, all the other variables, the sepal length, sepal width, petal length, and petal width, are predictors, so we can replace it by a dot to save space. And then we get a certain amounts of output. So let us try to understand the output. The first line is, of course, that are letting us know that we have used the knife-based function. The first part of output is the a priori probabilities. These probabilities correspond to this prior probability of the classes, the P of C. This is the probability that are assigned to each of the classes before encountering the data. So since all the three classes are equally likely, so we have 0.3 probability for each of these classes. Next, R is given the conditional probabilities. These probabilities correspond to these terms, the probability of x1 given C, probability of x2 given C, probability of x3 given C, and so on for each of the classes and each of the features. So probability, suppose x1 is sepal length and C is setosa. So the corresponding conditional probability is, if we go to the output, the sepal length and setosa. And then this is the posterior mean and the standard deviation of sepal length given setosa. So we have these posterior means of the values of the predictors given the classes here. Now that we have trained the model, next we can talk about the prediction. So remember that we set aside certain observations for prediction. So we are going to use the predict function on the test data. The first input of the predict function is the variable that stores the model. Remember that we use the classifier _CL to store the knife-based classifier. So that is the first input. And the second input has to be the new data, the test CL. If you do not put the new data, then R is going to use the same training data to perform prediction, which is not what we want right now. So on this test data, we can use the table function to compare the actual values with the predicted values. So overall, there are 60 observations in the test data. And we notice that all the 20 setosas were correctly predicted. There are 20 versicolors that were correctly predicted, and there are 17 virginicas that were correctly predicted. But 3 of the virginicas were predicted to be versicolors. So these are the rows correspond to the true class. So these three belong to the true class Virginica, but they were predicted to be versicolor. Now, if we look at the table, notice that all we are doing we are subjectively talking about the performance, that, hey, all the 20 setosas were correctly predicted, so that is good. 3 of the versicolors, or 3 of the Virginicas were predicted to be versicolor, so that's not perfect. But how to properly quantify the performance? So if we use a confusion matrix function that we are going to learn, that provides several criterion for model evaluation, like accuracy, which is a very common measure. So what accuracy is, it simply gives you the proportion of the total predictions that were correct. So here notice that 57 out of 60 predictions were correct. So the accuracy is 57 out of 60 as a percentage. There are also class-specific criteria like sensitivity and specificity that we are going to talk about later. So if we do the confusion matrix of this table, then we get the table and we look at the accuracy. Now, as you can see, there are several kinds of criteria that have been here. Two of the very popular ones are sensitivity and specificity, but that is class specific. What does it mean? So suppose consider the class setosa. Sensitivity means the proportion of actual setosa flowers that were correctly identified to be setosa. And similarly for versicolor and virginica, the proportion of actual positive cases that were correctly identified. On the other hand, specificity are the actual negative cases. So for class setosa, we are looking at the actual flowers that were not setosa, and we are looking at the proportion of these cases which were correctly identified to be not setosa. So as you can see here, for flowers that were not setosa, we have never made the mistake of identifying or saying them to be setosa. But for versicolor, in cases, for virginica, rather for versicolor, there were 3 cases where they were not actually versicolor, they were virginica, but we have predicted them to be versicolor. All right. Right now, before we move on to the next session, let us look at the naive-Bayes properties, and let's see if we can understand the basic idea of naive-Bayes through this online poll. So I would let this poll be raised, and there is only one correct option. Have a look at different options and see which one seems to be the wrong option. So can we please have the online poll? Maybe I'll put the poll myself. All right, so you can probably see the poll right now. And notice that we are talking about the incorrect option. Here, the attributes refer to the features or the predictors. Thank you very much for your participation. I'm going to end the poll now. So let us try to talk about the different options and see which one of the results are correct. So first of all, the attributes or the features can be nominal or numeric. The predictors can be continuous variables or they can be different labels themselves. For example, whether an email has the word buy or not. Now, of course, the idea is that the assumption of naive-Bayes properties is that the attributes are statistically independent of each other. That is the main idea of naive-Bayes estimation. And all the attributes are treated separately. We have all the attributes in our model because we take the product of the conditional probabilities for all the predictors available to us. So the only one that is wrong is that the attributes are statistically dependent, because under the assumption, that's the wrong status, wrong situation. So thank you so much for participating. So I'm going to start sharing the screen again. And before I move on to decision trees, I'm going to pause for a minute and let you ask any questions that you might have. All right. So are you all ready to move on to the next session? In that case, we can move on to the next classifier. Also, when I'm pausing for questions, please feel free to ask me to re-explain certain parts of the presentation in case some part needs to be re-explained or worked through in more details. Please feel free to ask me. All right. In that case, I'm going to move on to the next section. In the next section, we are going to talk about decision trees. Now, the decision tree is a very powerful and very popular machine learning technique, and it's used not just for classification, but also for regression. So the idea of a decision tree is that we continuously ask some yes, no, or a true, false, or an if-else statements, and we try to group the observations into several subgroups in such a way that in the subgroups, the data are all similar to each other. So let us try to understand what I mean by grouping the observations through this example. So suppose I have been told beforehand that an animal could be either hawk, penguin, dolphin, or bear. And I have to make a prediction on which of these four categories or classes a new animal is based on the features of whether the animal has feathers, whether the animal can fly, and whether the animal has fins or not. So notice that I first ask the question, does the animal have feathers? And if the answer is yes, I ask a second question. Okay, it has feathers, but can it fly? And if the answer to that is yes, then we understand that it must be hawks. But if it cannot fly, then we understand that it must be penguins. And if the if the animal does not have feathers, then we ask the second question, does it have fins? Yes, then it's a dolphin. If not, then it's a bear. So notice that before we started the decision, we had the hawks, penguins, dolphins, and bears all together. Once we have asked the question, do the animals have feathers? We have already grouped the hawks and the penguins in one side and the dolphins and the bears in a different group, right? And they are similar. What's similar? That the hawks and penguins, they both have feathers. The dolphins and bears, they do not have feathers. That's the similarity. And the next step, we further separate them. Can it fly? And then we can separate out the hawks and the penguins. And does it have fins? And then based on that, we can separate them into dolphin or bear, so that at the end, we are only left with bears. But suppose if we want to do a further classification, suppose black bear versus brown bear, then we can have a further question, maybe color of the fur. And then we can split them into even more homogeneous or similar observations, right? Based on the features that we have. So this is the idea of a decision tree. We are going to repeatedly split the observations into groups depending on the features. And then we are going to try to group the similar observations in a subgroup, in a region. Now, a decision tree usually is binary. That means at each time the question has a yes-no answer. So that at each time we have a if-else or a yes-no or a true-false answer. The most popular decision tree model is CART, Classification and Regression Tree. The basic idea here is that we are going to split the observations into different parts, and based on that, we are going to group the observations. There are two kinds of CART. One part is called classification tree, where the target variable is categorical, and one is regression tree, where the target variable or the response is continuous. So in this particular example, as you can see, is a classification problem. Now, a tree has a lot of very important components. For example, these decisions are called, these nodes are areas where we make certain decisions. So these are called decision nodes. The first node is called the root node. The last nodes are called terminal nodes. These are the outcomes. So these are the final groups that we achieve based on the tree. And these lines that join these nodes are called branches. So notice that from this decision node A, we have two nodes B and C based on the decision, right? So these nodes B and C are called the child nodes of A. And this node A is called the parent node of B and C. Now let us try to understand this concept of a decision tree with an example. Let us go back to the iris data. Now for visualization, I'm going to use only sepal length and petal length to be the two features. Now before we move any further, we need to install and load the rpart package. So please install it if you are working through. And we once again have a look at the iris data. We see that we are looking at the first and the third columns, the sepal length and the petal length, and we are still trying to classify the species. Right now I'm using the whole data because all I'm trying to motivate here is how the training of the decision tree occurs, or the classification tree in this case. So this is what the data looks like if I look at only the petal length and the sepal length. The red dots are the setosas on the left-hand side. The green little triangles are the versicolor, and the blue little squares are the virginica. The idea of a decision tree is trying to group these observations into regions based on the petal length and sepal length. So let us try to take an example. Suppose we are going to separate these observations based on petal length greater than 4 or not. So this is called a decision boundary, because if the petal length is less than 4, we are going to group the observations in one group. And if the petal length of the flowers is greater than 4, we're going to group them in a separate group. So if we group them together, so we have drawn a boundary here at petal length equal to 4, right? And notice that on the left-hand side, we have all the setosas and some of the versicolors. On the right-hand side, we have some of the versicolors and all the virginicas. So this is good, but can we do better? Can we really use this separation to separate out one of the species altogether? What about petal length greater than 2.75? Notice that on the left-hand side of this decision boundary, we exclusively have setosa. So based on this one line, we have already separated out the setosas from the other two classes. So this is a much stronger decision boundary. Next is that we have to separate the other two classes, the versicolor and virginica, because even though we have managed to separate out the setosa, we have not managed to separate out the versicolor and the virginica. But before that, think about if we used sepal length as a decision boundary instead of petal length, could we have achieved what we did with this red decision boundary? Could we have separated out the setosas completely from the virginica and the versicolor? For example, if we did y equal to 6 as our decision line, notice that all the setosas would be below the decision line, but so would be a lot of the versicolors and some of the virginicas. So that would not have separated out the 3 species as well, which is why petal length is more preferable here. Now, a little question for you. We have already separated out the sepal lengths, right? And we have these 2 candidate separators or boundaries to separate out the versicolors from the virginicas. So quickly, let us look at the next poll number 2, and where you are trying to choose the better decision boundary. So which of these 2 boundaries, the blue dotted or the green double dotted, which one of these 2 does a better job of separating the versicolors from the virginica? Thank you so much for your participation. I'm going to end the poll now, and let us look at the picture a little clearly and try to understand what's the difference between the blue line and the green line here. Notice that if we had only the blue line, we have most of the versicolors on the left-hand side, and we have most of the virginica on the right-hand side, which means that based on this decision boundary, I have grouped most of the versicolors on one side and most of the virginicas on the other side. So I have done a good job of separating out the two species. But think about the green line here. On one side of the green line, we have some of the virginica, but we have virginica on the other side as well. So we didn't really manage to group all the virginicas together based on this green line. Not only that, on one side, a lot of the virginicas are also mixed with the versicolors. So it didn't really separate out the versicolor from the virginica. So clearly, the blue separator is a better classifier. Now, what we worked through right now was, of course, by looking at it. But how does R do this? Well, we are going to use the decision tree or a classification tree in order to try to classify the iris data into the three parts: the setosas, the versicolors, and the virginicas. The function that we are going to use is called rpart. Now, this rpart function can be used not just for classification tree, but also for regression trees. The thing that changes is the method. If you are doing a method classifier, then we use method equal to class. If you are using the method regression, then we use method equal to ANOVA. We have more examples of classification because this is a classification session, but I also have a very important example on ANOVA further down. But right now, let us simply try to use the rpart function to generate the decision tree and see how it looks. The response here is, of course, the species, which is the class. And the two predictors that we use are petal length and sepal length. And it is stored in a variable fit. Next, we are going to try to plot the decision tree. Now, in order to plot it in R, we are going to use the power xpd equal to NA function. This is just to make sure that the text is clearly visible. Sometimes otherwise the text is clipped and the text is not very clearly visible. Next, we use the plot function with fit to plot the decision tree. And we can see that while we use the 2.75 using our I, they have used 2.45, which are pretty equivalent, pretty similar. And then once they have classified, notice that the left branch corresponds to an answer yes to the question petal length less than 2.45. Yes, then go to the left. If no, we go to the right. Once we go to the right, we ask the second question, is the petal length less than 4.75? Well, we used the separators 4, 5, and 6, but R has used 4.75. And then if the petal length is less than 4.75, we call it versicolor. And if it is greater than 4.75, that means the answer to this question is no, then we go towards virginica. Now, let us try to understand what happened here. So initially, since we are using the entire data for this training, we have 50 setosa, 50 versicolor, and 50 virginica. Once we group them based on whether their petal length is less than 2.45, we are left with only the setosas. That means we are left with 50 setosas, 0 versicolor, and 0 virginica. Next, the petal length is not less than 2.45. Then we ask the second question, is the petal length less than 4.75 this time? The question, and based on that, we call it versicolor. Notice that here, 44 versicolors have been grouped here, but 1 virginica has also come in. On the other side, if the petal length is greater than 4.75, we have the Virginica, 49 of them, but we have also 6 of the versicolors here. So this classification is not perfect, but we cannot really expect perfection in practice. So the question becomes, how did this algorithm decide where exactly to draw the boundary lines and how exactly to split the data? Well, there are multiple metrics available to decide how to choose a split. We are going to talk about one very popular metric called the Gini impurity. Gini impurity is used mostly for classification trees. So suppose that a given problem has k classes. So in this iris data example, k is equal to 3, corresponding to setosa, virginica, and versicolor. Now, when a split is being considered, what this algorithm looks at is the proportion of observations in each of the child nodes belonging to each of the classes. What does this mean? So let us look at the split, petal length less than or equal to less than 2.75. So once this split was made, its child node for this petal length is this node petal length less than 4.75. So this is the parent and the two children are this terminal node and this decision node. These are the two children. So when we started off, there were 50 in each class. And after the split, on the left child, we have 50 of one class and none of the other classes. And in the other child, we have 50 of versicolor and 50 of virginica. Let Pi denote the proportion of observations in class I for a specific child node. So the proportion of setosa in this child node is 0 out of 100. The proportion of versicolor in this child node is 50 out of 100. The proportion of virginica in this child node is 50 out of 100. So now we can calculate this formula. So for corresponding to setosa, we have 0. Corresponding to versicolor, we have half because it's 50 by 100. And corresponding to versicolor, we also have half. So we have half times of 1/4 plus 1/4. So the Gini impurity for this node is 1/4. The lower the impurity, the better the split. So we cannot just look at one child node, we also have to look at the other child node. What is the impurity for this child node? The proportions for the different classes are specifically for setosa 1, because it's 50 by 50, and it's 0 for the other two. So the Gini impurity for this particular child node is 0 plus 0 plus 0 is 0. So it's called a pure node, which is the dream for any classifier. So while considering whether to make a split, this algorithm looks at the Gini impurity of the parent nodes, and it looks at the weighted average of the Gini impurities of the two child nodes. And this weighted average is based on the number of observations in the two nodes. For example, there are 50 observations here and 100 observations on the right child. So based on that, it weights the two Gini impurities and finds a weighted average. Now, the question is, if from the parent Gini impurity to the average of the child impurities, if there is a significant improvement, then the split is made. And we compare the improvement for all the possible splits, and the best split is chosen. Right? So this is for classification. But for regression, we are not going to have exact classes here. We are going to have continuous values. So what we can do is we can look at the variance of the observations in each of the terminal nodes or each of the child nodes. So the lower the variance, the better the grouping has been done. So we are looking at the split with the best improvement in variance if we are doing a regression tree. Now let us try to understand and summarize what's going on in a decision tree. We are trying to divide the predictor space into several regions, right? For example, the three regions here are petal length less than 2.45, petal length between 2.45 and 4.75, and the third region is petal length greater than 4.75. So we have divided the features into three regions. And then for each of the observations that fall into these different regions, Rj, we make the same prediction. So for the region petal length less than 2.45, we always predict that the species is setosa. For the second region, we always make the prediction that the species is versicolor. And if the petal length is greater than 4.75, we always make the prediction that the species is virginica. So suppose there is a new flower with petal length 3. And if we have to make a prediction for that flower, we are going to first ask the question, is it less than 2.45? No, so we go to the right. Is the petal length less than 4.75? And we are going to see a yes. And so we are going to classify it as versicolor. That's the idea of testing. Now for regression trees, we make the prediction that is the mean of the observations. We are not going to have classes, we are going to have continuous observations. So our predicted value becomes the mean of the observations in this subregion. Now, for prediction performance metrics, we already looked at accuracy when we were talking about knife-based classifier. We can still use the accuracy as the proportion of the number of predictions that were correct. If we are looking at regression trees, we can look at the root mean squared error, which is, suppose you have n test observations and you have their corresponding predicted values. You look at the difference, that means the residual, and you square them for each of the observations. And then you take the average of these squared differences, which is called the quadratic mean, and then you take the square root. This particular metric is very standard in statistics literature, root mean squared error. Next, let us try to see if we can do a little bit of hands-on prediction based on some simulated data. So I'm not going to tell you how exactly I have, well, it's in front of you, but I'm not going to talk about in details how I generated the data. But all I'm going to tell you is that there are two variables or predictors, A and B. And based on that, I have split the observations into three regions: high, low, and normal. And I have trained a decision tree, and I have also split the data into training and testing. So we are going to use the training data, and this is the tree that we have obtained. So we are asking a lot of questions here. Is the B greater than or equal to 11.5? Is the A greater than 10.5? And so on. Remember that the yeses are the left branch. The no's are the right branch. So let us do one manual prediction using the tree. And I would let you guys try to look at this tree and try to understand how the questions are asked one after the other, and try to classify A equal to 8 and B equal to 8, and try to figure out what is going to be the level of this observation. So ask the questions here and try to come up to an answer by yourself. So I'm going to put up the next poll, and please try to make the prediction. Take your time. I'm going to give you a couple of minutes to closely follow the decision tree. All right. Thank you for your participation. I'm going to end the poll now and share the results. And let us try to understand how to work through the tree and how to come to a decision based on this tree. So we have A equal to 8, B equal to 8. All right. So we have the question B greater than or equal to 11.5. The answer is no, because the B is equal to 8. So we go to the right. And next we are going to ask, is A less than 9.5? The answer is yes. So we go to low. So we asked the two questions and we figured out how to make a prediction. But of course, as you can see, manual prediction is pretty tedious. So we are going to learn how to do the prediction through R. So we already have set aside some test data and we are going to make the prediction. So the predict function, when you are predicting a class, we have to mention type equal to class here. The first input is, of course, the variable that stores the decision tree, which is fit, and the test data was stored in a variable test. So if we simply look at the performance, we can see that A and B are the values, and we have the level, which is the actual levels, and we have the predicted values. We see that in most cases, we have predicted them correctly, but a couple of them were not correctly predicted. We predicted the highs as normal, and maybe we predicted one of the normals as high. Yeah, the normals predicted as high. And based on that, we can see that we can look at the table and look at the performance. If we want, we can also calculate the accuracy here. Next, let us try to perform the same work, but on a real data set. For this real data set, let us just focus on the training the model. So I'm going to use the entire data set for training. So this is a biomedical data set where we have 100 patients that are normal and 210 patients that are classified as abnormal. And there was 6 variables. The variable names are not given to us, and so we have v1 through v6 as the same as the variable names. But we know that v7 is the variable that is the response. So when we are doing the classification tree, notice that we again use the rpart function, and we are using the entire data set in this case. Though if you are comparing it with a different method, remember not to use the entire data set, but split it into a training or a testing. So we can use the plot function to have the decision tree, and we can make a prediction based on the same data set. So since we have since we have used the entire data set for training, what this calculates is the training error rather than the testing error. So you have to be careful. Since here there is no new data, this prediction occurs on the training data itself. So this accuracy here is the training error or the training performance. Now, I have written a little code here to explain what is accuracy. Remember that accuracy is the proportion of predictions that were correct. So this little R code here, the RPY-pred is the predicted value. The word $V7 is the actual label, the actual class. So this double equals to is a conditional operator. So the output of the RPY-pred equal to word $V7 are going to be zeros and ones. One, if this condition is met, that means the prediction was correct, and zero otherwise. So if I take the mean of these observations, it's going to exactly return to us the proportion of observations that was 1. That means proportion of observations that were correct. So this is a nice little trick in R to calculate the accuracy by yourself without having to find an appropriate package and looking at the accuracy. So all this time we have been talking about classification trees. Next, I want to talk about the regression tree with the help of an example, and we're going to focus on certain aspects to intuitively motivate the next part of this lecture. So suppose we are going to build a regression tree. We are going to use the Boston data that is inbuilt in R, but in a package mass. So when you're loading the data, you have to run Boston package equal to mass. There are 13 features here. There are 13 features which are used to predict the med-v, which this variable med-v is the median salary of owner-occupied homes. We are trying to predict the median salary of owner-occupied homes, and of course, this is a continuous variable rather than discrete. We are going to use these 13 variables to make this decision. Notice that earlier, so we are going to split the data, right? And earlier we had looked at the sample.split function to split the data. Here is a third way to split the data. It is called create data partition function, and we can split the data according to that. So far we have learned 3 ways to split the data. One is the sample function, one is the sample.split function, and one is the create data partition function. All right, based on this function, we can once again split the data into training and testing. We can still use the rpart function to generate the decision tree, but we have to put method equal to ANOVA, not method equal to class, because this is a regression tree. And for data, we have used only the training data. The fourth portion is something that I'm going to talk about later. We are going to motivate the importance of this fourth attribute later. But let us now look at the output. So we have plotted the picture here. The rep-r library function helps us to plot a nice plot on the R or on Colab. So based on that, this is the tree that we have. First of all, as you can see, this tree is extremely complicated. There are a lot of splits here. Lot of splits. And whenever you see too many splits, that should indicate that probably there is overfitting going on. That means the machine is trying too hard in its trying to capture all the similar observations, all the close observations. It's trying to find too many subregions, too many splits. So overfitting is a very prevalent problem in decision trees. It's very important to guard against overfitting. But before we learn how to control the overfitting, first let us try to see the prediction performance on the test data. We already have set aside some of the observations in test data for evaluation, and let us see how well this possibly overfitted model performed. So we use the predict function. We do not use type equal to class because this is a continuous prediction. And we can see that we have the actual values and the predicted values. And since this is a regression problem, we can use the RMSE function that we learned earlier in the session to calculate the overall performance. Now we can look at the RMSE function in the package metrics to find the output. You can also code it yourself if you want, but this is just an alternative where you do not have to code anything. You can use the RMSE function. And we see that 5.6 is the RMSE value. Now, just looking at the value 5.6, we cannot really say if this performance is good enough, or doable, or not good. We have to make a comparison. So let us try to understand first how to get rid of this overfitting problem. Notice that the problem here is the tree grew too much. There are too many branches. So we are going to cut this tree short, and this is called pruning the tree. Now, the rpart function has a lot of components in the control portion that allows you to control the number of splits and control the amount of overfitting. So when making a split, what rpart does is it measures some metric like a Gini index or lack of fit. And what it measures is that if there is an improvement in the Gini impurity or maybe the lack of fit from the parent node to the child nodes, then the split is made. However, we can make a threshold using the CP parameter, which means that we tell the model that unless that improvement is significant enough or greater than the threshold, please do not make the split. Earlier, what we had was CP equal to 0. So as long as there was some improvement in the Gini impurity or the metric used by the model, the split was being made, which is why there were so many splits. Now we are going to say that, hey, we are going to input a CP value, the complexity parameter, CP value, and we are going to say that unless the improvement is greater than the CP, do not make the split. So that is going to help us reduce the number of splits. But how do we choose this threshold? Because as you can see, if we use too large of a threshold, then the tree will be too small and the performance will not be good. If we choose too small of a threshold, then it is almost saying that as long as there is some improvement, the split is going to be made and there will be overfitting. So a good choice of the CP parameter is important. And this gives rise to the idea of cross-validation. The idea of cross-validation is how to choose this parameter CP that controls the overall tree structure. So this parameter, CP parameter, is also called a hyperparameter. And based on the choice of the hyperparameter, the model performance, the trained model is going to be different. Now, what is cross-validation? Remember that at the very beginning, we wanted to say that if we are going to evaluate a model, we do not want to evaluate the model on the training data, but on a different data called testing data, right? And the idea is that the training data is not a good indicator because it's going to favor overfitting models. So we train the model on some portion of the data and test it or evaluate it on a separate part of the data. So we have already split the data into training and testing. Cross-validation is a generalization of this idea. So for now, forget about the testing portion and think about only the training data. In this training data, we are further going to split it into training and testing. So it's like an added layer. What we are going to do is we are going to shuffle the data observations and then split the training data into K groups. So suppose there are 100 observations that have been jumbled together. Then the first 20 is the group 1. The next 20 is group 2. Up to the last 20 is group 5. So we have split the training data into 5 groups. As an example. Now, take one of these groups at a time and pretend that this group is the test data and the remaining 4 groups is your actual training data. Okay. Then we are going to train the model using only the 4 groups. So we are actually not using the entire training data, only 4 groups of the training data, and looking at the error on the 5th group, the group that we have held out as test data right now. And notice that this controls against the overfitting because we are not actually using this group to calculate the error. Next, we are going to shuffle the position. That means we are going to take the second group and pretend that the second group is our test group. And we are going to use the first group and the last 3 groups as our training data and find the error on the second group. And we are going to repeat this for all the 5 groups. So for a 5 group split, each of the groups act as the test data 1 time and acts as a part of the training data 4 times. That means k minus 1 times in general. We take the sum of or the average of all these errors, and these errors is corresponding to the current choice of the parameter CP. So suppose we take CP equal to 1, then we split the data into 5 parts. We look at the errors for each of the groups and we add them up. And we look at the total error. Then we take CP equal to 2. We repeat the entire process and we get a final error. And then we take different values of the hyperparameters and find which one gives you the best performance. Well, intuitively, it might seem that we are looking at the least error, but it's more complicated than that. But let's just say that we look at the best performance. There is a function called print CP function that gives you different choices of CP and the corresponding error using the cross-validation. So as you can see, you have several values of CP, and the X error column gives you the corresponding error that you make using the cross-validation. So you might be tempted to see that, hey, the least error is actually made by when I do not make any threshold. So why don't we use it? Well, let us have a look at the plot. In this plot, in the x-axis, we have the thresholds. Here we have infinite threshold, which is not something we want. And as we move from left to right, we have decreasing thresholds. And if we move Further to the right, we are going to get 0 as our threshold, which means that we do not do any sort of pruning. And on the y-axis, we have the error. The beauty, what makes this cross-validated error a good metric is because while calculating the error on a certain group, we do not use the group to train the model. So this error is free from the overfitting problem. That's what makes this so important, the idea of cross-validation. So we can look at these errors and we can see that, yes, the minimum point is probably on the right corner, but look at the horizontal dotted line. After we have crossed this horizontal line, is there really a significant improvement in the error? The answer is no. We can increase the threshold point from 0.004 all the way up to 0.0001. But that doesn't really improve that much, right? The improvement is almost insignificant. So the best choice would probably somewhere be around here, right after the horizontal line, but probably the leftmost or the somewhere between the second leftmost after the horizontal line. Definitely not here. So this is a qualitative decision that you have to take based on these plots. The plot CP function lets you plot this and try to understand which is the best choice of the CP. Now let us try to prune the data using 0.004 as our threshold. So we had developed the data already, the tree, using 0 as our threshold. Now let us try to cut this tree short by using 0.004 as the threshold. So we can use the prune function to prune a tree. The first input has to be the variable that stores the tree. The second variable has to be the thresholding. Next, once you plot the tree, notice that it's already much better. It's already much better. It's much clearer than a lot of splits have been taken care of, right? Now, using this pruned tree, let us try to see how good that we did. We looked at now a much more simpler tree with much less splits. How did it affect the performance? If we look at the RMSE now, it's 5.49. If you compare it with the earlier one, it was 5.6. So by considering a simpler model, we actually did a better job because the error is reduced. The error is reduced, so we have done a better job, which means that probably we did overfit the data when we were using CP equal to 0 while developing the first tree. This is why this is actually a very big problem of decision trees, that it is very prone to overfitting. And it is not very easy to get rid of all the overfitting. For example, it has to be a good balance between too simple of a model and then an overfitted model. The advantage of decision trees is that it's very interpretable. Very interpretable. We can see that, okay, we're looking at different variables and based on their values, we are grouping similar observations together, which makes the tree very intuitive. So this is where I've come to an end corresponding to this session. And before I move on to the next session on random forest, I would like to have a pause for questions if you have any. Remember that if you want me to explain any part again, you can ask me to do so and I will explain it. Or if certain explanations or clarifications were not clear, you can ask me now. Well, that's a great question. Well, the impurity does not depend on the number of observations, but rather how how the observations behave. For example, let us look at the impurity of this picture, the very intuitive picture of setosa, right? Now, if we look at the picture here, if we get more and more observations that are between, say, with petal length less than 2, even if there are 100 more observations, this classifier is going to classify all of them clearly as setosa. So that is not going to affect the impurity. But if we have more observations right near this boundary, with some of the versicolors going on the right-hand side, some of the virginicas going on the left-hand side, then that might increase the impurity. So it's not about the number of observations, but about the quality of the observations. Thank you so much. Any other questions? So by non-informative, that's a great question. That's actually going to be a part of my next section too. But even here, notice that in this model, when we use the iris data, we have put in two variables, like petal length and sepal length. Notice that sepal length does not appear in this tree, only petal length. The reason is probably the feature sepal length is not that good or not that informative with respect to making the classification. So this is why we have the Gini impurity that computes the best split for different features and chooses the feature that gives the best split. So this is how you can see which of the features are important for the predictor, for the response. By data, do you mean observations or like variables? Because, right. Yes, of course. You can do variable selection in certain ways. Well, there are more advanced techniques for doing variable selection, but in this way, you can realize from this tree that the sepal length does not really appear in this tree. And based on that, you can realize that sepal length is probably not very important compared to petal length. Does that make sense? Outliers. Well, outliers is a different issue. The idea of outliers is that suppose you have a setosa right over here, then this classifier is not going to be able to classify that setosa here. For example, there was a there was an error in recording the value, and instead of putting 2, it puts a 20, and you are going to get a setosa over here. But based on that, that setosa is going to be classified as virginica. So it is not very easy to identify outliers based on that, because it will be simply misclassified. So it's hard to understand outliers based on this example, at least, as you can see. So it's possible, but we have to do a little bit of extra work and maybe look at the problems. For example, for these 6 cases that were misclassified, we can look at these 6 cases and see were they outliers or were they just different shapes of flowers and so on. So we can look at the misclassified observations and check for outliers separately. But this is not by itself, a classification tree is not going to tell you that these are the outliers. Thank you so much. Thank you for the questions. In that case, I'm going to move on to the next section. All right. Random forest. So till now, we had a tree. Now we are going to have a forest. So lots of trees. That's the basic idea. Now, the idea of a decision tree was that we have only one tree that makes a certain decision based on certain branches, right? Certain nodes. However, these decision trees are often called weak learners, especially if you do not prune them, because they are very susceptible to overfitting. So the idea here is, instead of depending on one tree to give me a prediction, why don't I have several trees and then take an average decision? So let us think about the iris data example. So suppose we have decision tree 1, that was the data that we had, the tree that we had. And we have a new flower, and the first decision tree says that, hey, based on my decision tree, based on my questions, I decide that this is a versicolor. The second decision tree says that, hey, based on my decision, it's also a versicolor. Maybe 80 of the trees say that based on our decision, it's a versicolor. But the remaining 20 says, based on our decision, it's a virginica. So in this case, out of these 100 trees, we are going to say that since 80 of the trees said that this is versicolor, that is going to be our final decision. And this simple idea is random forest. Instead of depending on one tree, we are going to take several trees. Just as an example, take 100. And then we are going to take the majority voting for classification. And we are going to take the average of the predictions of each of these trees as the final prediction if you are doing a regression. Now, inside this very simple step of taking a lot of trees and taking the average are a lot of very little important nuances that need to be taken care of. First of all, think about it. Suppose that I used the entire data set of iris. Remember that I had used the entire data set of iris, and we built a tree. Now, I use the same data set and I keep building the trees. And we end up with 100 identical trees. That defeats the purpose of taking the average, right? Because if I get 100 identical trees, well, my final decision is going to be identical to their decision, because if the trees are identical, they are going to make the same prediction. That's not what we want. So in order to guard against that, there's a step called bagging. What bagging does is it slightly tries to change the observations for the different trees. So there are, say, 100, so there are, say, 5 observations, just for simplicity. If I use the 5 observations for all the n trees, they're going to be extremely similar trees. They're probably going to give the same prediction. So we are going to take a random sampling from these 5 observations with replacement. So suppose we have observation number 1, 2, 3, 4, 5, and from there we get a new sample, maybe of observation 1, 2, 2, 3, 4. This is called a bootstrap sample. So while we started off with observations 1, 2, 3, 4, 5, we ended up with observations 1, 3, and 4 once. We ended up with observation 2 twice, and the observation 5 never even appeared. right? This is called a bootstrap sample. Now, if I keep taking bootstrap samples every time, I am going to get a slightly different sample. Maybe next time I get observation 5, 4, 3, 3, 3, so that observation 1 and 2 doesn't appear. So for each tree, the observations are slightly different, and that's why the decisions are not going to be identical. And then we can take the aggregates. This is called bagging. Random forest goes even one step further. Random forest says that simply taking slightly different observations is not enough. In fact, the variables or features used in the trees are also going to be different. So originally, each of these trees or each of these bagged trees had all the features available for use, right? But the random forest, in each tree, we are going to use a subset. So suppose there are 4 features like sepal length, sepal width, petal width. Each time, we are not going to let random forest or each of the decision trees work with all the 4 features. For the first tree, maybe we choose 2 of them at random. So maybe sepal length, sepal width. For the next tree, we again choose 2 at random. Maybe we end up with petal length and petal width. So not only are the observations different, even the actual nodes are going to be different because the variables available to the tree are different. So this way the trees are completely more and more independent of each other. And this process is called decorrelation. And this way the different trees are working on different parts of the data with different features. And this is what makes random forest such a powerful method. This is very robust to overfitting compared to a decision tree. And that is what makes random forest one of the most stable machine learning techniques because of this aggregating, separating technique. Now so this is the idea of a random forest. Actually, before I move to the examples and how I actually implement them in R, maybe I'll take a 1-minute pause and let you guys ask me a question if you have any, based on the idea of a random forest. Is the overall approach or the process moving from a decision tree to a random forest clear? Even though I know we are not supposed to pause right now, but maybe I'll take a break and let you think about it a little and ask me questions if you have any. That's a great question. It might seem like a brute force approach because there are so many trees, but what this does is it takes an averaging approach so that the weird classifications of 1 or 2 decision trees that might be because of overfitting can be suppressed by the overall strength. So you can say that this is a brute force kind of approach because instead of working with 1 trees, instead of having a tree, we have a forest. And we are using the majority voting idea to suppress 1 or 2 bad predictions that might happen because of overfitting. Any other questions? In fact, with this idea of many independent decision trees brings us to our next point on how to choose how many trees to take and how to choose how many features to allocate to each of the trees, because that is going to affect your final outcome. And we're going to talk about that. Uh, Pictures. versus numbers. You mean the data sets corresponding to each tree? How different can the observations be? Okay, well, as you can see, you are still taking random sample from the whole data set. So they are not going to be completely different from each other. But depending, since it's a random sample, it can get pretty different. I mean, mathematically speaking, suppose you have 100 observations, you can get the 100th observation repeated 100 times. But we don't expect that to happen too much. What we expect is that all the data sets, all the data points are sufficiently represented in enough trees, and some of the observations are also removed. Some of the observations are also removed from each of the trees. So maybe in the first tree, observation 10 is missing. That is called an out-of-bag sample, for example. Absolutely. The number of trees, well, as you said, it's a brute force, so the more trees, the better. But of course, random forest is a slow method, exactly because of this. So it really depends on your computational availability. So usually 100 or 200 trees is what is used, but there is no fixed rule for the number of trees. The higher your model, your machine can handle without any issues is better. All right. Thank you for the questions. I'm sure that made it more clear for some of you. So I'm going to move on to the implementation now. So we once again use the iris data, and we once again, this time we use the sample function to split the data into training and testing. And we call the testing data as the validation data. In order to implement random forest, we use the package random forest. And the function is also named random forest. The overall structure of the random forest is very similar to the previous functions rpart and linear model and naive Bayes. That we have the species, that means the response, tilde the predictors. And we use the training data. Next, we have two hyperparameters, which is the number of trees, which is what we were talking about, and the number of features to select from the total number of features. Well, we have to remember that this iris data is a rather simple example. It has only 4 features, but in practice, there could be hundreds. And here the choice of mtry will become very important. Mtry is the number of features used in the construction of each tree. Right now, when there are 4, 2 of them, 2, 3, or 4, that's not very different from each other. We are still going to compare them for the sake of practice. But this choice, mtry, becomes the most important hyperparameter to figure out when you are working with a bigger data set. Also, importance equal to true. As someone talked about, if we can identify variables that are unimportant or non-informative towards the response, well, importance equal to true enables the algorithm to calculate variable importance. The variable importance is calculated exactly using the Gini impurity and other metrics. And it can order the variables according to the importance. So, all right, so if we look at the output of RF classifier, it gives an OOB estimate or error rate. OOB estimate is out of bag estimate. Now, out of bag estimate is slightly different from cross-validated error. It's actually a more computationally efficient version of cross-validation, because while random forest works, out of baggage estimate is supposed to be similar to cross-validated area, so that's the same idea, but it allows random forest to perform training and testing at the same time. What it does is it makes the random forest algorithm more efficient. So what is meant by out of bag is that Suppose once we are taking the bootstrap sample, suppose you have 5 observations, 1, 2, 3, 4, 5, and you end up with a bootstrap sample of 1, 2, 2, 3, 4. Then notice that while training this model based on this bootstrap sample, the observation 5 is not used. So if I find the error for observation 5, that is free from overfitting because that is not being trained by the bootstrap sample. So this error is called the out of baggage error, and this is repeated for all the observations throughout the algorithm. Anyway, but you can think of OOB estimate as some sort of an error rate that is free from overfitting. So it's a very reliable error rate. It also gives out the confusion matrix. As you can see, 27 setosas were correctly predicted as setosas, 22 versicolors were correctly predicted to be versicolors, and 21 were correctly predicted to be virginica. Now, if we make the prediction for the test or the validation data, we see that the performance slightly changes, and we see that the performance is very stable. It's 23, 26, and 23, and 3 of them were misclassified. All right. So as we talked about the importance of the choice of hyperparameters, so the choice of entry, the choice of M-try becomes very important. Now, entry, as you can see, the more the number of trees, the better the strength of the majority vote in suppressing the few wrong predictions that could be made by a couple of decision trees because they work with maybe poor features or maybe they overfit and they came off with a bad classification and so on. So there is a function called tuneRF function, which can help you tune the M-try variable, the M-try parameter, sorry, based on a certain number of trees. So if you fix the number of trees, and you can use something like step factor, which controls the steps by which the different M-trees are calculated. So M-try equal to 2, then 3, and so on. So step factor is 1.5. But in this case, well, it could be only real number, I mean, like whole numbers. So the improve is a parameter that controls that if the error is not improved by at least 1e negative 5, then the search ends. So as you move from say 2 to 3 to 4, if the improvement is not good anymore, then the algorithm stops. So if we plot the OOB error for the different M-tries, we can see that the best value was at 3. But the OOB errors for the different values are pretty similar to each other. But as just to remind you that this is a simple data set. In other cases, the choice of M-try becomes very important. So we can redo the problem with M-try equal to 3 to get the most reliable results. All right. Next, we are going to talk about a diabetes data set where we have different variables. And based on that, we are classifying the patients into different categories. Group 1 corresponds to overt diabetes. Group 2 corresponds to chemical diabetes. And group 3 corresponds to normal patients. There were five variables, and the ID is not that important, of course. These are the 5 features based on which we are trying to classify the patients. Now, here is an important distinction while we are doing classification. This is something R related. So in the previous case, the response variable was not just nominal, it's actually levels. These are characters, right? So it is easy for R to understand that these are not numbers, they have to be labels. But in this case, the response are group numbers, 1, 2, and 3. It is not that easy for R to understand that these groups, 1, 2, and 3, are continuous or discrete labels. Because Remember, in this case, even though the groups are numbers, they correspond to different labels. So group 2.5 does not make sense. So while doing the code, we have to mention it to R that this group must be treated as levels or as labels. So once again, we split the data into training and testing, and then we look at the random forest function. So notice that here I have put as.factor group to tell R that this group must be treated as a discrete variable. Based on that, if you make a prediction, you can see that we have the observed and the predicted values. And you can look at the overall accuracy to see, to check the quantitative performance. Now, before I move any further, let us try to do a little bit of a quiz about the properties of random forest. So notice that there are 4 options and one of them is correct. And you have to identify which of these 4 options is correct. So please try to answer the poll based on the understanding of random forest. Think about how random forest improves a decision tree and improves a bagged tree. Yeah, as you might have noticed that there are possibly 2 options. Thank you so much. I'm going to end the poll now. And let us try to talk about the different options and see. Well, there are 2 things that are possible. First of all, the individual tree is indeed built on a subset of the features that is controlled by the M-trial parameter. The individual tree is definitely not built on all the features. Next, notice that the individual tree is built on a subset of the observations simply because we are taking a random sample. So we start with the full set of observations, that's true, but we take not on a subset of the observations, but on a bootstrap sample of the observations, right? All right. So clearly, we do not have time to talk about the k-nearest neighbors approach here, but I didn't expect to have enough time for that. We're going to talk about k-nearest neighbor either in the next session or in the last session, depending on how we plan it. So before we end this section, I would just like to let you know that there are a few questions at the end. And although this question asks you to perform all the 4 methods, right now you can perform only the first 3. Please go through the codes and I will be providing the solutions within a couple of weeks. It will be on the website. And try to compare the different methods. On paper, it might seem that the random forest is always preferable to decision tree, but it is not always the case. It depends on the nuances of the observations. Even though random forest is probably one of the most powerful methods, most standard methods that for classification, but often the best practice is to try out different models, look at the prediction performance, and choose your model accordingly. And if each of these methods have their own pros and cons, random forest is extremely powerful, but it's very slow. Also, another problem of random forest is that it's not so easily interpretable. When we are working with one tree, it makes sense that, hey, we are splitting the predictor space, and based on the values of the different predictors or features, we are grouping together the observations and making a majority vote based on that. But when you have 100 trees on different features, different observations, and you take the aggregate, that result becomes a little less interpretable. So that is one of the disadvantages of random forest, that you cannot interpret a random forest. One tree is very interpretable and understandable. That is the advantage of a decision tree. Naive Bayes is important when you need fast calculations. Naive Bayes is, even though it takes a very strong assumption that the features are all independent, but it's a very robust method and it's extremely fast, because all you need to do is calculate the conditional probabilities and keep multiplying. So all these methods have their own time to shine. So the best practice is to understand the problem that you have and look at the challenges in the problem and see which of these methods work best. Yeah, that's right. That is correct. So, but there's a reason where random forest is heavily favored. Yeah, different models have their own pros and cons, and it's important to know the common ones at least. So I think that is the end of my session, and I would now pause for any questions. And otherwise, diminishing returns, well, not with respect to performance, but rather with respect to computational cost. As you get more and more observations, the results are the idea of, well, the idea of averaging becomes more and more powerful, because it can better suppress the outlying trees that are misclassifying or giving a bad results. But massive number of trees is preferable to a point after which it's more of a computational issue. But performance-wise, no. All right, so that's the end of my session, and I'm going to give back the session to Christina. Thank you so much for attending my session. Please respond to the post-survey and the pre-surveys that help me understand, and all of us understand, to prepare the sessions better and realize what exactly is required, which of the things we can focus on. Yes, I think the recordings will be posted on the website in the upcoming weeks. Thank you so much for turning up, but I'm giving it back to Christina.
Okay, thank you all for participating today, and thank you again, Dr. Dasgupta. Just as a reminder, our next session will be Thursday, January 20th, same time from 1 to 3 p.m. That session will be on statistical learning clustering, again with Dr. Dasgupta. Thank you all again.